Good evening, all. Today we are going to discuss about certain distributions concept which we use in machine learning, and we will also explore what are the probability theory basically working behind the scene while we start doing any exploratory data analysis, and what other various distribution strategies. So starting from the beginning, you can see that there are fundamental distribution approach like Bernoulli's distribution. Followed by that, we will also have a look on binomial distribution, categorical distribution, multinomial distribution, and at the same point of time, beta distribution. So let's have a look on what exactly is the binomial Bernoulli's distribution. And as you see that whenever we are going for any discrete distribution strategy for certain random variables, maybe which is having a binary output 0, 1 or true, false. Okay, so we generally make use of the Bernoulli's distribution approach. Have a look on the graph. So generally, if we take some real world examples like flipping a coin, so there might be a probability of having head or tail. So that can be very conveniently represent with the help of Bernoulli's distribution, isn't it? At the same point of time, whenever we start working with an aggregated results, isn't it? So we make use of binomial distribution. Like say, for example, consider the same example, we flip a particular coin with n number of times, and what exactly is the probability of having the head. So this is generally we are representing with the help of binomial distribution. So here again, you are getting two very important terms which we will be discussing now. Like one is known as the probability density function known as PDF, and another one is known as probability mass function that is known as PMF. So let me first discuss all the distribution approach, and then we will be moving into these two very important concepts which we use very frequently in machine learning. The next distribution approach, wherever we have k possible outcomes, because in the first two approach we make use of only two possible outcomes, either head, tail, or it is true or false. But in case of categorical distribution, generally we depend on n possible outcomes or k possible outcomes with probability given from p1 to pk, and this is how generally we can go ahead with a categorical distribution, because in certain data set you might have seen that yes, it's two specific outcome, or in certain places it is more than two. So we need to make sure that which specific distribution probability we are going to use for certain cases. So this is known as categorical distribution, where we have k possible outcomes, isn't it? Next to that, we have another distribution approach that is known as a multinomial distribution approach. It's actually a generalization of binomial distributions. As we have seen in binomial, there are two specific outcomes as it's reflected in Bernoulli's distribution also. So if we have a generic representation, that's basically known as a multinomial distribution, where instead of having two outcomes, we can consider k possible outcome at the same point of time. At the same point, there is another distribution approach we make use instead of having a discrete variable. Whenever you are using continuous random variable, okay, on a finite interval, we also make use of another approach that is known as a beta distribution approach. So these are all different type of distribution approach we have already seen. And now one most important thing we will be focusing, as I already told you, probability mass function. Okay, like when you are selecting X discrete random variables, and at that particular point of time, we always make use of probability mass function. And this is what exactly is the equation for finding out the probability mass function. So generally, PMF is used whenever you have discrete values, just like the example which you have quoted earlier, that we start flipping a coin. So there are probability of having head or tail for every instances. And when we start adding all the instances, and the possible outcome is represented with the help of a function, so that's generally known as the probability mass function or PMF, which is applicable for discrete random variables. And generally, if you would like to visualize PMF, we can make use of bar chart. Next, we will have another distribution function we use, which is completely based on density of data, as we have already gone through different machine learning algorithm where we make use of density as one of the prime concern. So we make use of probability density function, which is known as PDF. And here generally we consider a particular value, and that value is just a specific range. Say, for example, whenever we start finding out the probability of a specific height of any basketball player, and whenever we start predicting the same, so it's always better to make use of PDF, that is probability density function, because it always focuses on the relative density of data in a specific observed variable. So there are various ways generally we start make use of probability function. As I told you, one is known as PMF, which is used for discrete variables, and PDF is generally used for continuous random variable. Apart from that, another very interesting concept we use for estimation for non-parametric estimation strategies, and that's basically known as KDE or kernel density estimation. Because it's very, very important in certain situation, we always make use of a distribution strategy, and that distribution strategy comes from a non-parametric model. Okay, so based on a specific underlying data set, data points, the system can start figuring out the structure of a particular model. That is the main functionality of KDE. So generally, we can say that whenever we are making use of KDE, it's expected to have more data points surrounding that particular location, because once you have more data points, there is a high probability of having an observation to be true in that specific instances. So let's have a look at how KDE or kernel density estimation can be computed. So we make use of this particular mathematical formula to get kernel density, where we depend on three specific parameters. One is the location, the kernel function, and a specific bandwidth, which is playing a very important role in computing the value of kernel density estimation. So whenever we are talking about kernel density estimation based on this bandwidth version, we have two different categories of smoothing which we need to avoid. Like one we call as over smoothing, when your bandwidth is very large, so there can be a possibility of loss of information with underlying data, or it can be an under smoothing where your bandwidth is too small, might be reflecting a randomness over the corresponding underlying data points or data set. So that's what exactly we call that whenever we talk about the bandwidth. So we need to estimate the KDE with a very smooth distribution strategy. So we need to have an optimal bandwidth which is in between over smoothing and under smoothing, and giving us the proper estimation while we are working with any particular machine learning model. Let's have a look on this particular example. So we have taken an observed data set in the following way: X1, X2, and X3 respectively. And what exactly we did, we start calculating the value of Xi, and then we got the similar values over here as per the equation we have learned so far. We have taken a specific kernel function in the following manner, and ultimately we plotted the graph. And you can see that there are three different lines in three different points as we have considered. So in this way, once you start finding out the estimation, we will take the summation of the kernel functions at every point, and we got a kernel density estimation in the following way. So these are various estimation strategies we have learned, which is really important whenever we start working with a particular model to figure out which one is the best fitted model. So we must adopt the concept of kernel density estimation at the same point of time. Thank you so much.